if we consider an element of a group, it has an inverse associated with it, an inverse element, such that if we compose the element, the original element, with its inverse, we get the identity element. I'd like to show you that that inverse element is unique, that there is one and only one inverse element that can ever exist for a given element of a group. So what I want to show you is the uniqueness of the inverse element. And in order to do that, we'll use a proof by contradiction method. So first, we'll consider a group capital G and an element of that group, which we'll call lowercase g. So that's an element that belongs to the group capital G. And so I wanted to show the uniqueness of its inverse, the inverse of this element lowercase g. And if we use the proof, the contradiction method, we'll assume that the inverse is not unique, that there exists multiple inverses. In fact, let's say that there are two inverses, distinct inverse elements for lowercase g. So let h1, h2 be two distinct inverse elements of G, right? Such that H1 composed with, let's say dot, G is equal to G composed with H1 is equal to the identity element E. So E is the identity element. And this is an axiom of a group, right? So if we have a group element, lowercase g, and we combine it with its inverse, in this case H1, we'll get the identity E. And it doesn't matter the way in which we combine H1 then with G or G multiplying from the left on H1. The order is not important here. But since H2 is an inverse element of G, then we can also write that H2 dot G is equal to G dot H2 is also equal to E. Now let's consider the following expression, H1 dot G dot H2. So if G sandwiched in between these two inverse elements, these two distinct inverse elements, we like to ask, what is this? Well, one way to do it is to combine H1 with G first, and then whatever you get there, combine or compose it with what's remaining, H2. And so if we do it that way, well, H1 is an inverse element of G. So H1 acting with G from here would give us the identity. And the identity acting on H2 would just give us H2. So we see that this product of terms here, H1 dot G dot H2, gives us just H2. However, while that's true, from associativity, we can also say that this product of three elements here can be gotten by first composing G with H2 and then having H1 act on that. So if we do it that way, well, we know that H2 is also an inverse element of G. So G dot H2 is the identity element E. So G dot H2 here gives us just E. And this element H1 acting on E, being multiplied with E, so to speak. Now I'm using that word multiplication loosely. It's not well defined. It's a group multiplication. Could be an actual multiplication, could be an addition. It depends on the context, right? These elements could be matrices, in which case then the operation could be addition or multiplication, but it depends on the context. So H1 composed with E here, combined with E, would just give us H1. Well, now, if you notice that when we first computed the product of the three terms, we obtained H2. We did it the other way, we got H1. But like I mentioned, there is associativity that has to be upheld for any group, right? So these three elements, H1, G, and H2, are elements of our group capital G, and as such, they have to satisfy the associativity principle. And so it has to be true that H1 dot G, then composed with H2, will give us the same thing as having everything in the order that they appeared before, but just shifting the parentheses so that you have H1 dot this product G with H2. Right? This has to be true. And if that has to be true, then we're seeing that H2 has to be equal to H1. But this can't be, right? Because we assumed that the elements H1 and H2 were distinct, but not the same. Right? So because we have this contradiction, our premise can't be true. But if our premise can't be true, what does that mean? Well, if we can't have two distinct inverse elements, then we only have one, right? So that there exists only one inverse element for a given element of a group G. So implication here is that there's only one inverse element for G. Because if there weren't, you see that we obtain this contradiction that says that these two distinct inverses are equal to each other. That doesn't make sense. We can't have distinct inverse elements. We have to have only one inverse element. I hope that helps.